Okay, this is the third video for area between two curves. This time we're going to look at finding the area between two curves when the functions are functions of y instead of functions of x. And this can be helpful for finding the area between curves. Oftentimes when integrating with respect to x is difficult or requires multiple integrals, sometimes you're just going to have to use multiple integrals, but sometimes converting functions of x into functions of y can be helpful. So here it's pretty much the same thing as functions of x. It says the area between two functions f of y and g of y, and they're going to be continuous on the closed interval CD, where one is larger than the other, so f of y is greater than or equal to g of y. And that area is going to be the integral from definite integral from c to d, f of y minus g of y dy. So we can go ahead and draw a picture here. Again, we'll label our y-axis and our x-axis. So we can draw in our function g of y. So that's going to be our kind of our lower function. If you turned your head 90 degrees to your right, then g of y would be your lower function. That'd be our left function, and f of y would be our upper function or our right function. And then we're going to integrate from c to d. Okay, so we're looking at finding this area right in here. Okay, and so we're going to draw our representative rectangles again in this one, but they're going to be going horizontally instead of vertically. Okay, so we'll find a random y sub I in here. Okay, so it looks like I didn't label y sub I. So here's your y sub I. And so we'll have g of y sub I and f of y sub I. Okay, and so the height of that rectangle, well, it's kind of on its side, so I guess you can kind of think, yeah, we can still call it a height, or we can call it a length, I suppose. And the width of that we'll call delta yi, okay? And so it's the same idea as before. It's just instead of going rectangles up and down, we're doing rectangles right and left. Okay, so we use those rectangles to approximate the area. Now, the area of the yellow rectangle there is going to be, I guess you can think of it as the length. So f of yi minus g of yi times delta yi. Okay. The area between the curves can be approximated by adding up the area of all these rectangles. So that'd be the sum I equals 1 to n. F of yi minus g of yi delta yi. So then the area would be the limit. So we would let the norm of the partition go to 0. That'd be n going to infinity. Sum I equals 1 to n. F of yi minus g of yi delta yi. And then as long as that limit existed, we said that was the definite integral from c to d of f of y minus g of y dy. Okay. All right, so our next example here, oops, I'm going a little too far. Okay, so it says to find the area bounded by the graphs x plus y squared equals 12 and x plus y is equal to 0. Now, what's different than this than some of the previous examples is they told us specifically in the previous examples we want to go from x equals 0 to 2 pi or something like that, or 1 to 4. Here, they don't tell us that, so we're going to have to figure out where these functions intersect. Okay, so we'll go ahead and draw our xy plane for the time being, so your y-axis and your x-axis. And so we need to figure out where these two functions intersect. So probably it's going to be easier to solve each one in terms of y. So it's going to be x equals. So x equals 12 minus y squared, and that's going to be a sideways parabola with a vertex at 12 on the x-axis. And the other one is going to be x is equal to negative y, and that's just the negative identity function. So it's going to be a diagonal line kind of like that. Okay, so they're both equal to x, so they're equal to each other. So negative y is equal to 12 minus y squared. So this is a quadratic. Hopefully it's rigged to factor. This one is, so it's easier to factor or use the quadratic formula if your quadratic term, the y squared, is positive. So add y squared to both sides and subtract 12. Then cross your fingers at factors, so this factors into y minus 4 and x plus 3. So your zeros are y equals 4. So if y is equal to 4, right above that you have x is equal to negative y, so x is equal to negative 4. The other solution is y is equal to negative 3, and then again, x is equal to negative y, so negative 3 would be positive 3, so x is equal to 3. So now we have our points of intersection where these two graphs intersect each other. Okay, so now we just need to go ahead and graph it. Probably appropriate scale on the x-axis, since we are going all the way out to 12, probably 2 would be, going by 2s would be fine, okay? All right, so when y is 0, x is going to be 12, okay? And we're going to get a sideways parabola, all right? And so negative 4 to 12, we're just going to put that on there just to kind of help us out, all right? And y negative 4 is where we intersect on the in the x coordinates. Okay. All right. So there we have it. Okay. So that's your sideways parabola, and then we're going to put in your diagonal line like that. So again, we kind of drew maybe this much right here, and then you have the diagonal line crossing right there. So you're finding this area there. Okay. Now, there's two ways to do this. You can do it in functions of x, which I'll show you a little bit later on in the video, or this is easier to do in terms of functions of y. I'll kind of go through why it's easier to do in terms of y. All right, so then we're going to be doing representative rectangles, and they're going to be going horizontally. The upper function is always the parabola, and the lower function is always the line x equals negative y. Okay, now we're going to be integrating with respect to y, so our limits of integration need to be in terms of y, and then we're going to do the right function minus the left function. Okay, so the area is going to be equal to, okay, so we're talking about y, so where do they intersect? They intersect at negative 3, and they intersect at 4, okay, so those are our bounds for the y, so negative 3 to 4. The upper function, or in this case the right function, is 12 minus y squared. And the lower function is minus y. And we're going to integrate with that with respect to y. Let me go ahead and move this y here. I just wanted to label my y-axis, but we'll just put it right there. Okay, so the integral of 12 is 12y. Integral of negative y squared is negative y cubed over 3. And then we got double negative there, so that's going to be the integral of y, which is y squared over 2. Then we're going to integrate that, or sorry, we already integrated. We're going to evaluate that from negative 4 to 3. So 12 times 4 minus 4 to the third over 3 plus 4 squared over 2 minus 12 times negative 3 minus negative 3 to the third over 3 plus negative 3 squared over 2. Okay. All right, so 12 times 4 is 48. 4 cubed is 64, 64 over 3. 4 squared is 16 over 2 is 8. Then we're going to have double negatives, so you're going to have minus negative 36, which will be positive 36. Okay. And then we got like a lot of negatives going on. So we got 1 here and 3 there, so that's going to be 4. So that's going to be positive. And then this one right here is going to make it a negative. So it's going to be 27 over 3. Which is going to be 9, and it's ultimately going to be negative 9 or minus 9. And then 3 squared over 2, negative 3 squared over 2 is going to be 9 over 2, and then we're going to subtract that, so minus 9 over 2. Okay, so combining our like terms, 83 minus 64 over 3 minus 9 over 2. So get a common denominator here, which is 6. So 83 times 6. 498 over 6, 64 times 2 should be 128 over 6, and then 9 times 3 to get that common denominator is going to be 27 over 6, and so our exact answer is 343 over 6, or approximately 57.167 units. Sorry, not units cubed, We will be doing units cubed soon, but we are still at units squared. Okay, and then we'll go ahead and do this in terms of functions of x also. So it can be done in terms of in functions of x, but it may be a little more difficult. Okay. So first order of business is we'll just go ahead and resketch the same region here. Okay. All right, now we're going to be doing functions of x, so we're going to be going up and down instead of left and right. So we're going to be going vertically. We'll write down our two equations. X plus y squared is equal to 12. And it was negative x is equal to y, or is x plus y is equal to, I think that's what we had originally, right? X plus y is equal to 0. So yeah, that would give us negative x is equal to y. Okay. Now if we solve for y is going to be equal to, you're going to subtract x and then take the square root. So you're going to get y equals plus and minus the square root of 12 minus x, okay? And so we got two functions there. So the positive square root of 12 minus x is going to be the upper half of the parabola portion, and then the negative square root of 12 minus x is going to be a lower portion. Okay. And then we have the not quite the identity, the negative identity, negative x there. So if we kind of look at what's going on here, I got to represent a rectangle. The upper function is the square root of 12 minus x, and the lower function is negative x. So that's fine, not a big deal. However, once we get to here, when x is, I think that was 3, then our upper function is still the square root of 12 minus x, but now the lower function is negative square root of 12 minus x. So we have a change in lower functions there, so that requires a second integral. Okay. So the area is going to be from a negative 4 to 3. So this was 3 right here. X is equal to 3. Okay. Upper function is the square root of 12 minus x. The lower function was negative x. Plus, and then from 3 to 12, the upper function was 12 minus x, and the lower function was negative 12 minus x, and then both of those respectively under the square root. Okay. So that simplifies down a little bit. So negative 4 to 3, the integral of negative 4 to 3 of square root of 12 minus x, and then I'm just going to split it up. Okay, so using properties of exponents, so a double negative there, so we'll do its own separate integral for just the x. And then here we got a double negative, so that's going to be 2 of them, so we'll just slide the 2 out. So 2 integral from 3 to 12, 12 minus x under the square root dx. Okay, so we're going to be integrating 12 minus x twice. Well, let's go ahead and just do that off to the on the bottom here and integrate those. And I'm just going to do it generically. Okay. It's a u substitution. U is 12 minus x. Du is negative x dx. So negative du is dx. So this becomes the integral of u to the 1/2 times negative du. And so you can slide the negative out. And then just add 1 to the exponent. So 3/2 divided by 3/2 plus c. Flip the 3/2 over to make it 2/3, and then it's 12 minus x to the 3/2 power plus c. So we're going to go ahead and do that with both of our definite integrals involving the square root of 12 minus x. So negative 2/3, 12 minus x to the 3/2 power, evaluated from negative 4 to 3, plus x squared over 2, evaluated from negative 4 to 3, plus 2 times negative 2/3, 12 minus x to the 3/2. And then we're going to evaluate that from 3 to 12. Erase all that on the bottom there. Okay. So negative 2/3, evaluate, so plug in 12. So 12 minus, I'm sorry, not plug in 12, plug in 3. So 12 minus 3 to 3/2. minus 12 minus negative 4 to the 3 halves plus 1/2, and then that's going to be 3 squared minus negative 4 squared plus, well, actually, it's going to be a minus, isn't it? So we got the double minus. We don't have a double minus. We just have minus there. Okay. So minus 4/3. 12 minus 12 to the 3 halves minus 12 minus 3 to the 3 halves. Okay. And so we'll just continue this on the next page here. So there it is. Okay, so this is going to be negative 2/3, 9 to the 3 halves, minus 16 to the 3 halves, plus 1/2, 9 minus 16, negative 4/3, times 0 to the 3 halves, minus 9 to the 3 halves. Okay, so negative 2/3. And then 9 to the 3 halves is going to be 27. 16 to the 3 halves is going to be 64. Plus 1/2 times negative 7. Minus 4/3 times negative 27. So that's going to be 74 over 3 minus 7 over 2 plus 36. So common denominator here is 6. So 74 times 2 is 148 over 6. 21 is 7 times 3, so 21 over 6 is 7 over 2. And then 36 times 3, sorry, we have to multiply by 6 because we need a denominator of 6 there. So multiply by 6 over 6. Okay, 216 over 6. And so that's going to give us 343 over 6. Again, which is approximately 57.167 units, and it should say squared, okay, not cubed, should be squared. We're talking about just 2 dimensions here, so we're talking about an area. Okay, so hopefully you saw that integrating this one with respect to x was a little bit more difficult. Sometimes both are about the same level of difficulty. Sometimes one is significantly different, significantly more challenging. Just kind of depends on the functions, how difficult it is to solve for one of the functions. So you'll be using this idea of switching instead of integrating with respect to x to integrating with respect to y when you're going through different methods for finding volumes of solids revolution. So that's coming up in, I think, section 2.3. All right, so that's it for this video. We'll see you next time.